All right, welcome again to another one of Mr. Martin's math videos. This is a video for British Columbia Math 9. We're on Chapter 5, Section 4, looking at equations of linear relations. So by the end of this lesson, you should be able to determine the equation of a graph of a linear relation. So last video was gave the equation and we learned how to graph it, right, by coming up with a table of values. So today we're kind of working backwards. We're going to be given a graph and we're going to come up with the equation. Okay, how to verify the linear equation by substituting values and then match graphs to equations of linear relations. Okay, so if you have this first question, we're going to do a matching where we have to match the graph with the equation. All right. So, just like I said, last day we looked at how to use tables and equations to draw our own graphs. Today we're going to be working backwards, and starting from graphs, we will be determining tables and equations. But first, let's try a little matching activity here. Match each with its appropriate graph. So we have our three equations at the top here. Y is equal to 3x minus 4. Y is equal to negative 2x plus 5, and y is equal to 5x, okay? So in these equations, we always have to compare these equations to our basic equation of a straight line, which we know now is y is equal to mx plus b, right? With m being the rate of change and b being the original value, okay? The initial amount when x is equal to 0, okay? And that actually gives us where the line crosses the y-axis, which is really important and will help you kind of find with this matching activity here, okay? So here we have three graphs here, okay? A, B, and C, as seen below. For graph A, the line is from left to right. It's sloping downwards. B and C are sloping upwards, okay? And they're also crossing the y-axis and the x-axis at different places. But we'll see that the y-axis, the y-intercept, is going to be key here in some of these, okay? So now let's first start with looking at the rate of change, okay? You'll notice here that the rate of change for these, two of the rate of changes for these equations are positive, right? 3x and 5x, and one is negative 2x, okay? So based on these lines, which do you think would be the negative 2x, and which would be the positive 3 or positive 5 in terms of its rate of change? Just like we saw that there were two graphs that have, when reading the graph left to right, the lines are sloped upwards, and only one, when reading the graph left to right, is sloped downwards, okay? That kind of gives you an idea of what it looks like when you have a graph that's sloping down or a negative rate of change. We had a graph that gives us a graph that slopes downwards when drawn left to right, okay? So here, this gives us an indication of our rate of change here. Okay, so b, or y, is equal to negative 2x plus 5 would be equation or graph A there. Okay, because of that negative slope, the line slopes downwards left to right. Okay, and b and c could be the equation 3x minus 4 or y is equal to 5x. We have to figure out for b and c. Okay, but they both slope upwards, so those are positive slopes. Okay, those are positive rates of change. Okay, all right. Now let's look at the b values. Okay, the b values are also a help indication because we know that b is equal to the initial value of the relation, okay? And also, it's equal to our when x is equal to 0. Okay, we're going to add a definition here. It's equal to our y-intercept, okay, where the line crosses the y-axis. Okay, so we know already that the y-axis is this top axis here, right? Y-axis, 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 right? Our x-axis is these ones here, right? The horizontal is the x-axis, the vertical is the y-axis, okay? And when we think about the b value, it's the initial value when x is equal to 0. So where on the graph is x equal to 0? X is equal to 0 along the y-intercept. Okay, that's where x is equal to 0, right? X is equal to 1 here and 2 here, but x is equal to 0 along the y-axis, okay? So if we can figure out where the line crosses the y-axis, that's going to give us our b value, okay? So let's see here. What would be our b value here? Okay, when x is equal to 0, y is equal to 5 here, okay? So this tells me that y is equal, or b is equal to positive 5. Okay, what about this one over here? Here, when x is equal to 0, y is also equal to 0. So this tells me that b is equal to 0. And this last point here, the line crosses the y-axis down here. So when x is equal to 0, y is equal to negative 4. So my b value is equal to negative 4. Okay, so now let's look at our equations and see if we can find this, okay? A b value of negative 4, or let's start left to right, okay? So we're looking at graph A here just to confirm our answer that we had before. We already suspect that it's equation B, okay? But notice the b value here, all right? We have a y-intercept, we have a b value of positive 5, and that matches what we have in the equation, okay? So this is confirmed, all right? Let's look at our next equation here, or our next graph here. Graph B gives us a b value of 0. Okay, well, which of these equations have a b value of 0? The answer is C, right? Here, because there's no plus or minus anything, that means b is equal to 0. So C would be this graph here, all right? And for our last graph, C, we have a b value of negative 4, which matches our A equation here of negative 4. So A, follow the line. Let me try to, okay, would be that graph there. Okay? Another way that you can look at, you can confirm this is to use test points, okay, which just means to plug in numbers into the equation to see if the points that you get are on the line. Okay, so for example here, when I plug in, let's say x is equal to 1. If I were to plug x is equal to 1 in this equation, I'd get y is equal to 3. I substitute 1 in the place of x, minus 4. Y is equal to negative 1. So I should have a point on a line of 1 and negative 1. Okay? So let's see if I do. On this graph here, graph A, 1 and negative 1 is like, well, it goes down by negative 2.5. So it would be like here, this point here. And you see that this point is not on the line. So this can't be the right graph for equation A. Over here, 1 and 1 looks like it's, at this position here. Again, that's not found on the line, so that can't be the right equation for it either. And then here, 1 and 1 lands right there, and it shows up on the line, so that tells me that the equation and the graph match, okay? It's not a bad idea to use 2 separate points, not just 1 point, just to be sure, right? So y is equal to, maybe I'll plug in 2 now. minus 4. That's going to give me y is equal to 6. That's 2. So 2 and 2. This should also be on my graph. 2 and 2. And sure enough, 2 and 2 shows up right there. So that confirms that the equation and the graph match. Okay. Same thing with this one. I'll just use 1 and 2 again. Negative 2, 1, plus 5. Y is equal to 3. So 1 and 3 should be a point. And y is equal to negative 2 times 2 plus 5. Y is equal to 1. So 2 and 1 should be a point on this graph here. So let's confirm. 1 and 3 and 2 and 1 should be here. Okay, so 1 and 3 is about there. And then 2 and 1. Now, because it's a scale of 2.5 here, it's a little bit sketch, but those points both show up on my graph. And they also don't show up anywhere else, right? 1 and 3 would be like here, and 2 and 1 would be like down here. 1 and 3 is like way up here, and 2 and 1 would be here. And so those don't fit, those points don't fit any other graph, so we confirm our answer there once again. And last one, just to be sure, y is equal to 5, 1, which is equal to 5, and then y is equal to 5. Plug in 2 in the place of x, y is equal to 10. So 1 and 5, I should have a point. And 2 and 10, I should have a point. So on my graph, 1 and 5, I have a point here. And 2 and 10, I have a point here. They both show up on my line. So again, I've confirmed that the equation of the line and the graph match. Okay, so lots of different ways for you guys to do this, to figure it out, and to double check your answers to make sure that you've gotten it right. Okay, my work's kind of gotten messy, but hopefully I've given you guys enough tools and enough different approaches to this, both understanding the equation and looking for the key points, or also just plugging in values to x and then seeing if those coordinates end up on the line of your graph. Okay? All right. So let's look at an example here, starting with a graph and then working backwards to a table and then an equation. So concept 1, determine a linear equation from a graph. Now let's try to work backwards. Here we're going to be given the graph and we're going to try and find the equation that describes its behavior. Great Slave Lake, which is located in Northwest Territories, is the deepest lake in North America. It has a maximum depth of 614 meters, okay, more than half a kilometer deep. Sam decided to check the depth up to 108 meters, which was the maximum depth that his fish finder could read. So this is the data that he got on his fish finder, okay? So so the two variables here are distance from shore and water depth, okay? And so here we have our independent variable, right? And dependent variables, okay? So the depth of the water is going to be based on the distance from the shore, right? We know lakes typically, they get deeper and deeper the further they are from the shore, but it's not the depth of the shore, the depth of the lake that's going to tell you how far you are from the shore, okay? So one is dependent on the other, okay? And we have data here, okay? Obviously at 0, the depth is 0, and then it increases by 10 on this side, okay? And we see here on this side, it decreases by 35, right? 35. Okay? And it looks like this on the graph. When you graph it, our first points, 0, 0, end up here. 10, negative 35 is here. 20, negative 70 is here. 30, negative 105 is there. 40, and negative 140 is there. And 50, and negative 175 is there. Okay? So they plot the points, they connect the lines because we know that this is a continuous relationship, okay, between the points. All right. So here, how do we determine the equation, or what linear equation does this graph represent? How do you know the equation matches the graph? Okay, so again, we have our basic equation, which is y is equal to, mx plus b, okay? Knowing again that m is my rate of change and b is my initial value when x is equal to 0, okay? All right, so here my rate of change in this situation, or my rate of change is a fraction, okay? My rate of change is that it's going to go down negative 35 meters depth, increase by 35 meters for every 10 meters from the shore. Okay, so my rate of change is this fraction of negative 35 over 10. Okay, we can reduce this fraction to negative 7 over 2. Okay, just by dividing the top and bottom by 5 there. Okay, so I have a rate of change that's a fraction here. So for every 2 meters from the shore, you're going down 7 meters. Okay, so for rate of change here, another definition that you can put, it's the change in the y values or dependent values over the change in x values. Okay, we've been doing this all along. However, in previous notes, our changes in x values were always just changing by 1. And so whatever the change on the right was of our dependent variables, it was just over 1. And so, the fraction over 1, you can just ignore the 1, right? But we were doing this whole time. So, but we always need to have it. So we always need to have our rate of change as a change in y over a change in the y values over the change in the x values. Okay, like I was saying before, when this is changing by 1, and let's say this was increasing by 3, we just said that the rate of change for a relationship, like if I were just to draw a quick table here, 1 and or 0, 0, 1, 3, 2, 6, right? Our rate of change for this, we would have said was 3, right? But if you look carefully, here it's changing by 1s, here it's changing by 3. So what we would have actually, what we actually wrote, but we didn't show, was that our rate of change was actually 3 over 1. Okay? For every change in x values, and then change in y values. Okay? However, when your x is changing only by 1, you have a denominator of 1. You can kind of disregard that. So that's why we ended up with a rate of change of 3. Okay? Now this is a rate of change for this hypothetical table, not the table above here. Okay, this is just an example of me showing you guys. This would be the rate of change for the table above. Okay, we take the change in the x values in the table, which change by 10, and that's our denominator. Our numerator is a change in the y values, or change in the dependent values, which is negative 35, and then we reduce our fraction. Okay, so that gives me my m value. Okay, now what about the b value? B is equal to the initial amount, right? The initial value when x is equal to 0, all right, and also the y-intercept, right? That's the other definition that we have here. Lots of definition. They all give you the same answer. I forgot a piece of the word there. Intercept, there we go. So lots of definition for us for the b value. And so here, they're all here. The y-intercept is right here, which is when y is equal to 0, right? We have a y-intercept of 0, 0, which matches what we have in the table here, right? When x is equal to 0, y is equal to 0. So we would have a b value of 0. Okay, so my equation for the line then would be y is equal to negative 7 over 2x plus 0. And of course, that plus 0 isn't necessary, so this would be the equation of our line. Okay, based on the graph. Okay, now let's see if we can use this equation to solve for some of these questions. So if this pattern continues, how far from shore would sand be when the water was 614 meters deep? So here, is this the y or the x? Oops. Is this the y or the x variable they're giving us in this question? Depth of water, you remember, is the y variable. It's the dependent variable. So they're giving us here is the y. Okay, and they're asking us for the x, right? How far from shore? That is the x variable. So here I'm going to substitute. I have my equation of y is equal to negative 7 over 2x. And I'm going to substitute 614 in the place of y. And then I'm going to solve for x. So I'm going to divide both sides by negative 7 over 2. All right. And here, it's important, this depth, 614 meters deep, this would give me a y value of negative 614 meters. Okay? If you look at the graph, depth is plotted as negatives. Okay? So that's an important point there, because we were going to end up with a negative distance from shore. So I have negative 614 divided by negative 7 divided by 2, or just negative 3.5 if you prefer. And I get a distance from shore of about 175 meters. All right. At what rate is the depth of the water decreasing? So here we saw, based on our m value, that it is decreasing negative 7 meters for every 2 meters depth, okay? Or you could say negative 3.5 meters deep per 1 meter per meter from shore. You don't have to say 1 per meter from shore, right? We can simplify that even more. Negative 3.5 if you prefer. You could have done that up here as well as your rate of change. That would have been fine also. Now here, last question for this example. Is it appropriate to interpolate or extrapolate values on this graph? Explain. First, is it appropriate to interpolate, yes or no, on this graph here? Can we assume that the values between the dots are true values? Yeah, right? Like if you see it going down by a straight line, at 25 meters from the shore, we would assume that, the depth is about here, right? And at 35 meters per shore, it's going to be about here. Maybe not exactly, but, we can assume that. Okay, that's a safe assumption. Okay, so yes, we can interpolate, no problem, yes. Okay, what about extrapolate? Okay, here we can extrapolate a little bit because we know that the maximum depth of the lake is 614 meters, which is quite a bit lower, right? So we could probably extrapolate a little bit. However, could we extrapolate forever? Right? Is the lake infinitely deep? The answer is no, right? The lake is not infinitely deep. The lake is only 614 meters deep. So at some point, the line is going to level off, right? It's not going to stay, and not at this point, right? But if the graph was larger, the line would level off. And if you think about the depth of a lake, right? If this is my shoreline and this is my lake, the depth of the lake kind of, usually rounds at the bottom. Not everywhere, right? But it can be deeper, go deeper in a kind of a constant rate at first, but then it kind of just levels off, and the rate at which it gets deeper changes. And so to extrapolate would not be appropriate in this situation. Okay, so we wouldn't want to extrapolate because we couldn't assume that the rate of change was going to stay constant. Cannot assume that the rate of change would remain constant forever. Okay, so interpolation, yes. Extrapolation, no, not infinitely. All right, your turn. Okay, so I want you guys to try this question out on your own. First step that you're going to do is you're going to take the data from the left side here, plot it into the table, and then from the table see if you can determine the, based on your equation, y is equal to mx plus b. See if you can determine the equation from the line. So first take the points on the graph, fill them into the table, and then from the table, find the m and the b value and substitute those values into your equation. Go ahead and pause the video and work on that, and then unpause when you're ready to go over it together. All right, hopefully that went well for you. Okay, so here I have all these points that are given to me on the graph. Okay, so I'm going to put these in my table of values. Okay, however, x and y, right? However, here they don't start at 0, they go up by 2, and so I'm going to give myself a point, like a spot for 0, okay? Because it's just helpful, especially when I'm looking for that b value, to leave space for the 0 when possible, and in this situation, it's possible. So, and I'm just going to import these points, the 2 and the 3, the 4 and the 4, and put them into my table. So when x is equal to 2, y is equal to 3. When x is equal to 4, y is equal to 4. When x is equal to 6, y is equal to 5. When x is equal to 8, y is equal to 6. And last one, when x is equal to 10, y is equal to 7. Okay? So, here we see that x increases, by 2 each time, and y increases by 1 each time. Okay? So, if I were to go back here to 0, all right, it goes by, backwards by 2 to get that 0 point. Let me just redraw this. If I were to go backwards, I'd have to go -2 to 0. Here I'd have to go -1. So I'd get a 0 and 2. Okay, so that helps me find my b value. All right, so, and let's see if we can come up with our rate of change. Okay, again, we're looking for m and b from the data that we've put into our table. Okay, now m, again, my rate of change is equal to the change in, let me just rewrite that, change in y values over change in x values. Okay, and here, change in y values, we saw the y values change by 1. They increase by 1, okay? And the x values change by 2. So I get a rate of change of 1 over 2 or 0.5 if you rather, okay? So that would be my rate of change, either fraction form or decimal form, okay? And then my b value, which is the initial amount or initial value when x is equal to 0, also my y-intercept, but on this situation that's not applicable because the line does not give me a y-intercept. But I can see when x is equal to 0, y is equal to 2. Okay, I was able to determine that based on how the x changes and the y changes. Okay, so b is equal to positive 2. All right, so now I just plug in these values. Y is equal to 1 over 2 x plus 2. All right, that would be the equation of your line based on the data from the graph. Okay, so just like we went from the equation to a table, then to the graph last video, this one we go from the graph to the table and then to the equation. All right, so you're just working backwards. Think about the steps you learned last video, apply them here. Okay, now we're gonna look at comparing graphs of linear relations here. All right, and what it looks like when, similarities and differences. So the first thing that we're gonna look at for this, the two questions we're gonna look at is how are they the same, and then how are they similar or different? Okay, so these two lines here, the green line and the red line there, okay, what is the same about these two lines? What is the same? They both have the same what? Hopefully you're able to see here that they both have the same, use a bracket here, both have the same y-intercept, which would also be they both have the same b value in the equation. Okay, they would both have a b value of plus, that looks like plus 3. Okay, so that's one similarity. I'm sure there's other similarities you can think about. They're both straight lines, blah, 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 but that's kind of the similarity that's key for what we've been talking about today. And how are they different? Well, they have a different slope, right? So they're going to have a different, they have a different steepness, right? One is facing, left to right is going up, one left to right is going down. So they both have, I'll just say they have different, we call it slopes or steepness of the line. They have different slopes, or they have different rates of change. Okay, because for the green line, as the x variable changes, as your independent variable changes, your green line, the y values decrease. But for the red line, as the x values increase, the y values also increase, right? When x is equal to 1 for the red line, y is equal to 7. And when x is equal to 2, y is equal to 11, But for the green line, so the y values increase as the x values change. But for the green line, when x is equal to 1, y is equal to 1 as well. But when x is equal to 2, y is equal to -1, right? So they're decreasing. So they have a different rate of change. So with that in mind, again, we're kind of going to work backwards. In this space below, sketch a graph with two lines that have the same m, so the same rate of change, but different constants, different b values, okay? In this graph here, they had the same constant, same b value, but different rates of change. In the space below, I want you guys to try to draw, or on a piece of paper, draw two lines that have the same rate of change, but different constants, okay? All right, so hopefully your lines look something like this. So because they have different b value or different constants, they have to have different y-intercepts. So I'm going to have one line cross my y-intercept here and another one cross down here. Okay? However, now the rates of change have to be the same. So essentially here, the steepness of the line has to be the same for both. So let's say I were to pick a pattern that said, okay, every time I go over to the right by 2 blocks, I go up by 1. So I get this kind of shape here. Okay, And I want to have the same rate of change for the line below. Okay, so I'm going to draw the line below in green. Okay, so every time I go over by 2, I go up by 1, and I get these dots here. Hopefully you guys can see them. All right, so let's, connect the dots here for these shapes. I'm going to zoom out a little bit because, there we go. All right, so we get a line like this for the bottom. No, I don't want that. I want to keep it green. Okay, there we go. And I want a line like this for the red. Okay, and notice, no. Stay red. There we go. Notice that these two lines are parallel. Okay? That's how you know that they have the same rate of change. Okay? Is that it will give you two lines that are parallel to each other. Okay? So same steepness, same slope, okay? But they're just starting, one above the other. Okay? But they're both changing by the same amount. As the x value changes by 2, the y value changes by 1. As the x value changes by 2, the y value changes by 1. Okay? So that's how you would answer that one. So hopefully, by the end of this video, you feel comfortable being able to determine an equation of a graph of a linear relation, right? First, you go from the graph to the table, then to the equation. You can verify linear equations by substituting values. Okay, we did that right from the beginning of our notes, substituting values. And then the last one, you can match graphs to equations. And then that was, again, at the very beginning, we did that matching activity. All right, your homework assignment is here, and that will be posted in Teams for you to submit. Hopefully this video was helpful to you. Put comments below if you have any questions, or contact me directly if that's an option for you. And stay well.